Yeah, thank you, Henry, for this kind introduction. Yeah, so Manfred Stöcker, he asked me to give a lecture about my work I did in Argentina, and it mostly comprises the use of stable isotopes in the modern setting, so water-stable isotopes, but also we went to the paleo record and used a proxy material where you have a recorded source of precipitation, of paleo precipitation at that time, so to look at the environmental conditions at certain periods back in the past. Okay, so here you have a very nice view of the upper Calchaquí Valley, and in these valleys you have a very large fill of sediments that range from Oligocene times to the present, with several filling phases, and they are very rich in paleo-environmental information that hardly nobody studied yet, but also it contains a lot of tectonic information. And my work as a PhD student here in Potsdam was actually putting both these things together. So this climatic information with the stable isotopes with tectonic information that we know about the region. So the topics we will cover today is, first of all, I will introduce you to stable isotopes. What are stable isotopes? To the methods, the concepts and pitfalls of stable isotopes. I heard you are a quite diverse group of people with different backgrounds, so I think this is a good start. Then I will show you next a case study where we looked at the modern isotope elevation relationship in the Andes. And then finally, I show you some results here in the third part about the landscape evolution in Argentina and also the paleohydrologic evolution of the South Central Andes. Here below you have a very nice diagram of, in a nutshell, what we did. So we first looked at, defined the modern relationship of delta D versus elevation. So here in the x-axis elevation, but here you go up in elevation into the origin. And then we used stream water, stable isotopes, that are these points here, where we looked at different elevation about the isotopic composition of the stream water. But then we also went into a basin record here and actually looked at the evolution of this kind of transition from a foreland setting and incorporation into the origin itself or into the plateau. And that is then if you use a paleo record to do this. So what are stable isotopes? Here is just a list of the commonly used stable isotopes in earth sciences. So we have hydrogen, carbon, people are looking at nitrogen, oxygen, and sulfur. And some of them are, so most of them are stable isotopes, so that means they are not decaying over time. But here, as you can see, there are some stable, so there are some isotopes like carbon-14 that most of you probably know are decaying over time and have a certain half-life. So in this talk, I will mostly talk about the hydrogen stable isotope and about oxygen stable isotope. So if you look at the relative abundance of these isotopes, you can see that most of the isotopes, in this case oxygen, is in the form of 16O, and compare that to 18O, or here in the upper part where you have the hydrogen, where most of is like hydrogen 1 with 1 neutron, and then you have the heavier with 2. So how do we use these isotopes then to decipher about elevation changes and also climate? And this is actually, the concept is actually shown here in a nutshell in this slides. So in general, if you have a temperature gradient, so from high to low, and you have here on the x-axis is plotted elevation or even latitude, so you have a temperature gradient. the ratio of delta 18O or delta D in precipitation are usually mimicking this kind of linear relationship with temperature versus elevation or latitude. Stable isotopes are measured as a ratio, so you have a standard over your sample, and your sample, your ratio is then the heavier isotope, for example here 18O over the lighter 16O, or your deuterium over oxygen, and usually it's the notation is in per mil, so that means parts per thousand. So it's very small differences that you actually look at when you do stable isotopes analysis and to look at the ratios of stable isotopes analysis. So here as a quick example, if your initial air mass has, say, an isotopic composition of -10 per mil, you have a temperature gradient here along the orographic front, your air mass rises, it rains out, so the heavier isotopes actually precipitating because it's heavier versus the lighter, so the lighter preferentially rains out. So leaving the air mass that actually remains actually more depleted, so meaning that it has more of the lighter isotopes. So in that case here at the top, when you have your rainout along the orographic front, this air mass here at the top is actually lighter or more depleted. So if you still haven't fully understand the concept, this is another slide to illustrate that. So the ultimate source of all the water in the world is of course the ocean. So with you have evaporation of ocean water where you actually it's feeding up into the higher air masses. And if this air mass, for example, then is transported and hits an orographic front, for example, you start to produce first uplift and condensation. And again, the heavier isotope preferentially condensate, forming precipitation, for example, in this example here of -3 per mil. The vapor is then more negative because it lost the heavier isotope. And then this air mass is traveled further, it rains again, of course, then the precipitation has more depleted isotope values, and then this process goes on. So how did we started to recognize all these processes? And this was done in the 50s, actually, with a network of meteorologic stations worldwide. So at each station, people started to analyze the water and the isotopic composition of this water. And first, people were interested to only monitor nuclear bomb tests, but then researchers later in the 60s and mostly Dunsgaard actually looked at these data more systematically, and he realized that there's a very nice correlation between temperature here on the y-axis, temperature on the x-axis versus the isotopic composition of the rainwater that's falling at each station. And here you could see this kind of very almost linear relationship between temperature and the isotopic composition of the rainwater. So this network actually was then expanded quite a lot, and today this is the modern kind of distribution of GNAP stations worldwide. And the headquarter where all these GNAP stations actually are coordinated coordinated is actually located in Vienna. So there's a headquarter where all this information from worldwide is actually combined, and you actually can access this data through their website. So it's open source. So if you're interested, you can download each station, and each station consists out of like monthly to daily data of delta 18O and delta D isotopic compositions. So this is open source, so you can download it through the website of the EIA, so the Atomic Agency. And if you would plot up all this data, and this is done here in the next slide, you can actually see the global distribution of delta 18O worldwide. And here it's already quite interesting. So the The warmer colors are actually less depleted, where actually more the bluish, greenish, and then the pink colors are actually much more depleted. You see actually quite nice trends already by looking at this data set. So first of all, there is one effect that's called the continentality effect or continental effect. And this is quite visible here if you go, for example, from Europe into Russia and actually into the Arctic. And because you actually rain out your water that's derived from the Atlantic over time as the air mass trajectory is going eastward, and you lose a lot of water and precipitation, and that's why the stable isotopes are much more depleted. And there's a second effect, and this is more on shorter distances, and this is the elevation effect. For example, if you look here at India, if you go up in elevation, you see over a very short spatial scale, quite large changes in delta 18O, and this is due to elevation, the impact of elevation that's then related to temperature as you go up with elevation. On this slide, you see a plot of delta 18O versus delta D or hydrogen. And usually, if you have an air mass that travels along a trajectory and rains out, all this depletion actually follows a 1-to-1 line when you plot up in the deuterium and oxygen space. So this is the so-called global meteoric waterline, and here you can see it has the deuterium has a slope then defined as 8 times delta 18O plus 10. However, this is the ideal case, so this means an air mass that doesn't recycle, it continuously is moved and rains out, it follows this line. However, there are a lot of times complications when you go back into the past. So, and this is shown on this diagram here. You see that, again, the global meteoric waterlines. So, for example, if you have your air mass right here, you actually go up and rain out. So you have transport and rain out in the so-called continental effect. However, evaporation, for example, if your rain is falling and evaporating as it travels to the surface, you actually can deviate from this global meteoric waterline. The same is true for continental transpiration. So if you think about that in the Amazon area, you have a lot of plants, the rain is falling, and as it falls through the lower atmospheric levels, this is actually taken up by the plants through transpiration processes, and then it changes this original isotopic composition following the global meteoric waterline. So as a first summary for this part, I showed you that the temperature is the main driver of stable isotope fractionation. That in an ideal world, oxygen and hydrogen isotopes plot along the so-called global meteoric waterline, and that the water isotopes are very susceptible to environmental conditions, so meaning evaporation can change your isotopic composition. So if we go now to the second part, and this is the first case study where we looked at modern stable isotope distribution in the Andes. And so this means, we sampled along here the rivers at different elevation and looked at the isotopic composition. And ideally, we hope to get this kind of relationship where we're getting more depleted isotope values when you go higher up in elevation. So just again to remind you again, so temperature goes down with elevation, so that's why the ratio of delta 18O or delta D should follow this kind of trend. However, here in the lower part, if your air mass is traveling and then again it travels away from the source, however, if it interacts with another air mass with lighter isotopic composition here from below, the air mass above again is enriched again. However, this is not classical Rayleigh fractionation, meaning that it follows a global meteoric waterline of depletion. So our motivation in the Andes was mostly trying to understand why we have such a poor fit of delta 18O or delta D at high elevations. For example, if you look here in the upper part, here in Europe, you see that there's a quite good fit between the oxygen on the y-axis and the elevation on the x-axis. And then here the same in North America, and of course it's very good for extreme latitude where you have a large temperature gradient. However, here in the lower part, when you go to higher elevations, you see that the fit is quite poor, and it's not so well understood why these fits are so poor. So each single wiggly line here represents one stable isotope study. So I would say in Europe and North America and extreme latitudes, we understand what is going on. So here you really have this Rayleigh fractionation. However, here in the case of the Himalayas and the high altitude, you see these poor relationships, and we don't understand really what is happening here. So we went to the Andes to look at the stable isotope distribution along this very large topographic gradient here, and also in precipitation. It's here these greenish colors here in front showing a lot of vegetation. However, if you go up on the Puna, and this is a view looking west, you can see that the higher parts of the Altiplano Puna are actually very dry. And then on the back side, you have the Atacama Desert. That's one of the driest places on Earth. So to introduce you to the topography and climate of South America, so our study area was located here in northwest Argentina between roughly 22 to 28 degrees north and south, and 64 to 68 degrees west. And you can, if you look at the precipitation pattern in South America, you can see that the winds from the Atlantic brings moisture into the Amazon basin up here at the upper part. So it's the system is a so-called South American monsoon that brings moisture into the Amazon basin. However, there's a second transport system that brings this moisture along the orographic front into northwest Argentina, and this is the so-called South American low-level jet, or short SALI. So this is really bringing a lot of moisture into northwest Argentina, and we wanted to understand what is happening when this moisture is actually penetrating along the orographic front and onto the plateau. Another important thing in South America, and that's what a lot of people forget, is actually what is happening at higher elevation. We know the plateau is today around 3.8 to 4 kilometers, so we really have to worry about higher atmospheric levels, because this is only showing the wind patterns at elevations of 1,000 meters and below. At higher elevations, and this is shown here, we have a large high-pressure system sitting off to the east of the Altiplano Puna Plateau that actually circulates wind around from the Amazon basin towards the Pacific, and then this wind is actually going across our study area with quite large wind speed. And at the same time, you see this kind of gradient here in wind speeds actually increasing if you go southward. So this has very dramatic implication if you then look at the distribution of vegetation and also precipitation. And this is shown in this very nice ESA image that was taken in April 2014. And again, you see all this moisture that the South American low-level jet brings into that part of northwest Argentina. You can see that this moisture tries to penetrate further into the origin and onto the plateau. However, at the same time, you have this kind of dry upper level airflow over the Andes. And just for orientation, if you're always used to looking at Argentina north-south, this is flipped to the side. So this is like south is towards the left, and towards the right is north. And at the same time, you see, if you go further down in South America, you see this kind of humid westerlies bringing a lot of precipitation to the west side of the continent. However, then on the backside of the Andes mountain range, there's a huge kind of aridity effect because of the sinking air masses that actually are depleted in moisture. So again, here on the red, this is where our study area is located. And this is a zoom in of our study area. And so again, so 28 degrees south, going all the way up to 22 degrees south, here towards the north. And so if this moisture actually is coming down along the Andes and actually is transported here into northwest Argentina, it encounters the first barriers and uplifts of the Andes. And there you produce quite high rainfall amounts. However, the backsides, as you can see by the more reddish colors, are quite arid, with precipitations of less than 200 to 100 millimeters per year of rainfall. So I will show you, just to get an idea of this, like two spots, two images, one taken here south of just west of Tucumán, and one on the more arid side, on the lee side of this orographic barrier. So just in front of these orographic barriers, you have very lush vegetation with a lot of trees, almost a jungle type rainforest growing. However, as you just cross this orographic barrier that very effectively captures all this moisture, the backsides are usually quite dry and there's just some shrubs growing and small bushes, but it's very arid. And this is again shown very nicely here on this image, where you're having these really greenish colors on this side, where this represents the Yunga type vegetation, the so-called rainforest vegetation here in northwest Argentina. However, the backside, as you can see, they are quite arid. So we sampled along these three transects here. So our transect 1 is this is our transect 2, and transect 3, stream water in very small catchments. And these catchments are usually like 15 square kilometers and less. And that is very important, because if you're sampling huge catchments, it's hard to interpret the signal that you get derived, because you really need to know where your source or where your rainfall is falling in the catchment. So if you have a small catchment, you can very precisely say at what elevation this precipitation is falling. So here on the next slide, these are all the results from all three transects I showed you in the previous slide. We sampled from 2010 all the way up to 2013, so over several years, but always in December, January, February, and that's where most of the precipitation falling. It's like 80 to 85% of the precipitation is falling over this time period, and the summers usually you have very little precipitation here. So again, you have your global meteoric waterline here in the dashed line, and then you see how these data is actually seems to be following this kind of depletion along this line, so showing really that you have some Rayleigh fractionation. However, you see already some complications. So for example, all these round circles here in our transect 3, they are plotting just all at one location. And that becomes much more clearer what this means on the next slide when you plot this isotope data versus elevation. And this is shown here. So in our first transect here, so our transect 1 in the north, you can see that there is some relationship. So on the x-axis, it's mean catchment elevation. On the y-axis is delta 18O. And here in the north, you see some correlation between mean catchment elevation and delta 18O. However, if you go progressively south towards transect 3, you see that there is hardly any relation. So you see that it's invariant. So at 4 kilometers, you have pretty much the same values as at 1 kilometer. So this means that there is no isotope fractionation with elevation in the most southern transect. And this is really expressed by the lapse rate here shown in red. So we try to model and see how would an air mass look like that would go up and progressively rain out over each transect. And this is shown here in red now. So this is our predicted model run here. In red, the solid line and the 95% confidence interval of our model. And you see that here in the northernmost transect, you see like a decent fit. However, some data actually falls out, and that's probably because you have runoff of higher elevation waters into lower elevation where we then sampled. However, here in the most southern transect, you see that there is no correlation at all. So the question is really, what is going on here? And especially when you plot that against latitude and bin this at elevation, and this is shown on this slide here, you can see that at low elevation here, higher latitudes here, you see that all data plots at one location. However, if you go further north, you see this kind of spread in data indicating really that you have much stronger isotope fractionation here towards the north. And so what is the reason for that? And of course, that's then next, that the Bolivian high plays a very important role, and especially this kind of airflow over the Andes from west to east. And what is happening here is that and this is shown in this cartoon here, that in the most southern transect, you actually have a setting where actually this warm, humid air that's has a lot of moisture actually wants to go up in elevation and go on top of the Altiplano Puna Plateau and rain out. However, at the same time, you have this kind of westerly airflow over the Andes that sinks here towards the foreland, actually suppressing the rise of the lower air masses. And what happens is that you actually have an inversion layer building right at the interface where actually this air mass is actually trapped below and in these intermontane basin zone. However, at certain times you see, and for people who have already been in Argentina, you will experience a lot of convective storms occurring. And further south you go, so stronger these convective storms will get. So what is happening here is, and this is actually what is causing these convective storms, is actually when you have a weakening of this easterly dry airflow, or you have very intense heating in these intermontane basins. At night, this very hot and quite energy-rich air mass actually is able to break through this inversion, and then there is rapid kind of convection upward, and then rainfall that is falling in these areas. However, as I showed you, you need to have some lateral transport in order to promote isotope fractionation. However, if you have these convective storms occurring here, you don't have isotope fractionation because everything is, the air mass moves up, and at the same time the rainfall is occurring right at this location and everything comes down again. So this is not the classical Rayleigh fractionation what I showed you in the introduction. So in this we observed in a very nice deep convective storm event in 2011. So in the morning we had this kind of inversion in place. So you're actually looking westwards towards the Altiplano Puna Plateau. This is this Santa Maria Valley, and these clouds were just banked here along the margin of the Puna, and that's how this looked. The setting looked in more towards the foreland. However, later on, as we were climbing at high elevation to collect water for stable isotopes, we saw actually a very particular event occurring. And this is that air masses here at the lower part, where you actually have like this kind of topographic low, was moving towards the Puna. So air mass was sucked into these intermontane basins, where all these other clouds were actually moving the opposite direction. So really showing you this kind of inversion setting. So a lot of humid and very energy-rich air was advected into these orographic intermontane basins. And then you had this kind of very dust storms occurring in these intermontane basins. And then suddenly you have this kind of, at night, this kind of rapid convection. You see huge cumulonimbus clouds. and that then you had thunderstorms and massive flooding at that night here. So this is the process that's occurring here, but can we quantify this process a little bit better? Because now I showed you, okay, this process is occurring here, this is important, but can we quantify how important it is? And this is what I will show you on the next slide. So this is, we use for that TRMM satellite data. And so TRMM stands for Tropical Rainfall Measuring Mission, and we use the time series from 1998 till 2012. Unfortunately, the TRMM satellite is down now, so it's out of service. It just happened a year ago, so that's a little bit unfortunate. However, this time series was more than sufficient to quantify these convective storms. And you have different sensors on the satellite, and I will not go on all these details, but we use the precipitation radar, that usually has a cell size of 5 to 4 kilometers. And so if we looked at this time series, and this is now here in the upper part, this is actually the days going up, so this means 1998. And then until 2012, and each day has a number. And then on the y-axis, you see the rainfall intensity over this complete 10-year, more than 10-year time period. And you see that there are a couple of events with very high intensities and producing a lot of rainfall. So if you plot this as a histogram, and that's shown here in the lower part, you can see that there's a lot of small events occurring that actually have very little rainfall intensities that are expressed in millimeters per hour. However, then you have these very large or big events that produce a lot of rainfall. And you can see that almost 95, so if you say this is 90% of the data that produces rainfall, that only 10%, what's remaining, produces tremendous amount of precipitation, really, that is controlling the hydrology in this area here, because these storms are producing most of the precipitation and rainfall, and that then is, you can see as a runoff in the area or refilling these aquifers. So we plotted now, so you can use this and say, okay, where is our 95 percentile limit? And this is shown here on the next map, how important they are. So comparing your higher end of the, sorry, let's go back, really showing how important the end tail of the distribution is compared to the beginning or the start of the tail. So here is a map of all of South America, and this is like the 90th over 15th percentile ratios. And you can see, so in general, lower numbers mean there's less convective storms, and higher numbers mean that this kind of large events are dominating the whole rainfall distribution. So you can see here that in in northwest Argentina, you see quite high values of 10 to 15 to all the way up to 15. And whereas you go to the Amazon basin, these convective storms are less important. So this is really showing that this is dominating the rainfall distribution in South America, these really intense convective storms. And of course, then this will be recorded in the stable isotopes. So this is now a zoom up of the area. Again, our three transects here. And you can see here that especially in the more southern transect 3, you see very high values of this 90th over 15th percentile of rainfall. And these convective events are then really fueled by all this heat stored in these intermontane basins. So this means there's heat available at night that can actually drive this kind of convection. And you don't observe these kind of basins when you go further north. So there's some kind of interplay between intermontane basins that form, and these convective storm events. So to just clarify this a little bit more and show you as a transect, here's only shown the northernmost transect versus the southernmost transect. This is again use the topography along this transect here. This is the mean topography, max min. And then also the 90th or 15th percentile, that's our convective storm intensity parameter. And you can see already that it's almost twice as high as in the Rohrmann transect. If you superimpose now the rainfall distribution onto it, you see, for example, that here you have a large peak where you have high relief, also high rainfall amounts. So that this is what you would expect when air masses can rise along topography and rain out as it's uplifting. Here in the southern part, however, you see where it's the highest relief, the rainfall amounts are actually dropping, so really suggesting that something is prohibiting the rise of the air mass and rain out. And now, just to sum this up, so this is really the isotope values, again here from reddish color showing more enriched isotope values, where darker colors or showing more depleted isotope values. And here you see that you don't see any correlation with elevation at all, where here in the north you see that the lowest values you have in the foreland, and then when you climb in elevation, of course, you see that the isotope values are also reducing. So what are the implications for this? So first of all, if you look at stable isotope models, that modeling the isotope distribution in these areas, you see already that there is a mismatch. So these models suggest isotope values between -10 to -8 per mil, where we only find isotope values of -4 to -6 per mil. And if you think these are small changes, just to remind you, if you do paleo-elevation studies, 2.4 to 2.8 per mil is like interpreted as 1 kilometer of elevation change. So these are important differences. So, and in general, all these models don't capture these kind of regional atmospheric convection occurring in these areas, so really showing that these models need higher resolution to capture these events, and also to that these model runs are then improving if the resolution is higher, and that these kind of inversion settings are captured by these events, by these modelings exercises. So the area is insensitive to capture elevation changes. So if you work in the most southern transect and you want to use stable isotopes to say something about elevation changes in your paleo record, this is probably not a good idea, because a 4 kilometer elevation looks similar like as 2 or foreland setting. So you cannot really discriminate between both these two things. So if we step back and look now at the regional isotope distribution, and this is a summary also using Gonfantini's et al. 2001 data, and recently there's some more data published. You see that, for example, you see this kind of trend along the Andes when you go southward. So in Bolivia or north of the band, you get at a certain elevation. I only plotted data at circa 3 kilometer elevation. You see that the isotope values are quite negative, showing that in that elevation north of the band, you get isotope values between -18 to -15 per mil. However, if you go southward and along the Andes, they can become more enriched, and this is really due to these convective storms that are increasing as you go south along the Andes, and then this inversion setting that becomes more important. So as a summary, so I showed you that convective storms in general, first of all, weaken the isotope elevation relationship. These storms mostly form in intermontane basins, and of course, if you want to do paleo elevation in these areas or using with different proxies, if it's from lake to proxies in sedimentary sections, these you run into a problem here. So, and that's a very important takeaway message here. So, the second point is really that the paleo elevation reconstructions relying on water isotopes might be compromised, especially not only in Argentina, but also when you go to different areas worldwide. For example, a prime location would also be in northwest India, where it's also these convective storms occur, and there's a similar setting. So as in general, if you're interested to pursue or maybe think a little bit more about it, as a research recommendation, it's really important to examine the global link between convection and isotope composition, because it has not been done yet. So especially in other plateau regions, and especially how convection changes under future climate, because there's more and more energy available in the atmosphere, meaning that there's more convective events occurring or will occur in the future, but we don't know yet how, and especially also how these stable isotopes will behave under such a setting. So let's leave that part behind and come to the last part of the talk. And this I will go now into a paleo record. So we actually look at the landscape and landscape evolution, and also especially the paleohydrologic evolution of the South Central Andes. So I showed you that at certain parts there is a stable isotope elevation relationship, but in other parts there is not, especially in the most southern part. And of course this has important implication when you work in paleo records. So in a paleo record, a good approach to actually look at changes between two locations is actually when you have a record at the foreland setting. So this is like a sedimentary core or a record in the foreland, and then you compare this to a setting onto the plateau, because they should see the same climate, they should see the same kind of changes over time. And the only changes then, if you see a differences between a setting on the plateau and a setting versus the foreland, then is elevation. So this is actually shown right here. So this is, if you can rule out climate, then the only differences between that two settings then can be interpreted as an elevation difference. So if you work in a paleo record, you have a whole sort of options of what proxies you like to use. So there are many different ones. So my work mostly involved organic proxies or lipid biomarkers and pathogenic carbonates. And Heiko Pingel's work was all around volcanic glass and the isotopic composition of volcanic glass. But you can also use teeth and bones to reconstruct the environmental water at that time. But you can also use metamorphic minerals in fault zones that actually, when fluids actually migrating meteoric fluid down these fault zones, and then are incorporated in metamorphic minerals. So you have a huge option of proxy materials you can use. However, I will only talk today about the pathogenic carbonates and also organic, so the lipid biomarkers, and a little bit about the concept of volcanic glass, because I think this is most of you are interested in. So in general, pathogenic carbonates are forming when soil water evaporates, and it forms calcium carbonate precipitates around objects, and these can be twigs, these can be stones, this can be small materials, so like a nucleus, and around this nucleus soil carbonate carbonate starts to precipitate. And this usually occurs in equilibrium with the soil water, so this means the environmental water that was present at that time as the carbonates were forming. And this is just to illustrate you that at certain depth, up to 1 meter, you form soil carbonates. So the second proxy is, and that's my proxy I used during my PhD, was organic compounds and leaf waxes. And here I used analcanes, and analcanes are actually waxes that the plants produce to protect themselves for evaporative loss. So if you touch a leaf, and it's usually this kind of waxy material on top of the leaf, and these are really analcanes. However, there are also, you can form analcanes in aquatic settings with bacteria that also don't want to lose water to the outside, and they protect themselves during analcanes. And analcanes are carbon bonds. So for example, in this case, this is a carbon chain, and at the end of each chain pair, you have attached hydrogen. And this hydrogen is derived from again from the environmental water at that time, so in order that you can analyze it. But just to show you, there's a whole bunch of other biomarkers that you can use. There are alkanoic acids that are quite popular to use, or sterols and hopanoids. They are all just to show you different biomarker proxies that can use that have advantages or disadvantages versus analkanes. However, the nice thing with analkanes is really that it has been shown that analkanes usually form in equilibrium with rainwater delta D. And this is shown here by a study by Sachs et al. In 2012, where he shows a compilation here where you can really see this kind of nice one-to-one relationship between the rainwater delta D and the delta D that is then preserved in these analkanes. So this really shows that today in the modern, these analkanes are tracking the isotopic values of rainwater that the plant is using to grow. So just to show you a little bit how this method works, is usually you have your soil or your plant or your sediment, and you actually, if you have a sediment that's quite hard, you need to crush it first and you create a powder. You actually, after that, you use actually like an extractor, and this is here an accelerated speed extractor, that it's an oven where the sample goes in, and then there's organic solvent that's flushing through the sample, and this then the liquid that's what it's flushed with is then collected in the vessel below. Then you have to do some chemical treatment where you mostly actually separate the different biomarkers, so you have a clean fraction with only analkanes in it. Then you quantify your analkanes using GCMS, so a chromatography, and then you measure on a mass spectrometer then the hydrogen isotopic value of the hydrogen that is attached to the carbon. All right, so the last proxy I promised you to show is really the delta D of hydrated volcanic glass. And this is, so for example, when you have a large eruption, there is glass, it's silica, that's actually erupting out of the volcano, and with the ash clouds actually transported laterally and with the wind. And usually as the glass is erupting, it contains hardly any water. It's like less than 0.1 weight percentage of water. However, so this is like water starved. And over time, when this settles and the rain is falling, this glass is acting like a sponge. It actually wants to suck in water that actually it bounds it in the pore space of these hydrated volcanic glass. And this pore space, it's very stable, and the glass, this water is then trapped in this amorphous material. So this is just to illustrate you, that's how this looks under a microscope, your amorphous glass. Again, there's very little weight percentage of water during the eruption. However, after saturation with the environmental water, it contains 3 to 5% of water. So really showing that it's neglectable, the first starting composition of the water during eruption. And then usually it's very stable again, and it's only if you heat it to high temperatures you can actually lose this original delta D composition. And the same is actually true for the biomarkers. You really need to heat it to more than 100 degrees to lose your isotopic composition. So here, again, it has been also shown that there's a linear relationship between the isotopic composition of the glass and that environment it was collected, and then the environmental water. Okay, so now we are ready to go into our paleo record, and this is the kind of concept we like to apply. So we go now first to a foreland setting and look at the isotopic composition in our foreland setting. And a few words about the structural setting, and you probably have heard a little bit during previous lecture about it. So in northwest Argentina, you have this kind of broken foreland setting where you actually have block uplifts that are uplifting and actually dissecting the foreland. And it's different than what it's observed in Bolivia, where you actually have this nice propagating fault and thrust belt, where you're actually having anticlines forming and actually propagation of the thrust belt over time eastwards. However, this is not the case here in northwest Argentina. So we were interested in what is happening when these kind of block uplifts that act then as orographic barriers are actually changing the paleohydrology, vegetation, and moisture supply to the backsides of these uplifts. And what are the timescales involved in these processes? So just to show you, we have a setting here where we have the plateau. We have the intermontane basin setting right here in the middle. And then, of course, the foreland when you go out towards the east. Now I show you just a cross-section here where it's indicated in red across the area with time. And this combines all previous studies looking at thermochronology and constraining the uplift history of this area. And this incorporates our section we went into and looked at in the Angastaco Basin. So first of all, at 10 MA, we had indication of cooling and uplift in an area west of our study area that's located right here. So this was our active orographic barrier at that time. However, later in the game, we had here towards the west uplift of another orographic barrier. And that then reached critical elevation actually and then acted as an orographic barrier. And the backside after that it actually starts to fall dry. And then this is the setting today where you have then growth of these structures here more towards the foreland and then filling of the sediments here on the backsides of these uplifts and then aridification of the hinterland over time. So we went into the Angastaco Basin and looked at a sedimentary section here, and that's shown in black. And just to show you how the section looked like, so this is a very nice section. You have actually tilted bed, and this is quite scenic when you go there. This is called the Angastaco Basin. And you have like very beautiful dipping beds where you can just work your way along this kind of transect when you go from east to west in this picture. And the nice thing in this section is you have like a lot of intercalated ashes in these sediments, and that has many advantages. First of all, we get a good date of this ashfall, so we have very good age control. Secondly, we use then this volcanic glass proxy to get a delta D composition of the rainwater that's falling. And then we can compare this with our biomarker proxy and the delta D that's contained in that. So this is now the stratigraphy and the section I measured. And this is more than 2.5 kilometers of section. So here at the base, you can see that the section has an age of roughly 9 million years. And then if you go up, you get we had several ash beds that Heiko Pingel dated. And what you see here plotted in green is actually the samples of the lipid biomarkers, and in orange, the soil carbonates. And in general, if you just look at the stratigraphy, you can see already that you see kind of fining upward sequence in this part, where here in the middle part of the Palom Pintado section, you have very fine material. And then again, if you go towards the top, you see a coarsening upward in the section. So again, you see a fining upward, but then a coarsening upward again in the section. And again, so the basin today is located at 2 kilometers. So in the Palo Pintado section here, there were previous studies that reported a lot of fossils in these beds. So for example, they found alligator fossils that actually indicate that this area was not higher than 500 meters in the past, but then also a lot of leaf imprints and also pollen data that suggest a similar vegetation as what you find today actually in southeast Brazil at very low elevation, not more than 500 meters. So this is already very consistent with a low elevation setting as the Palo Pintado formation was depositing. So here are some plant fossils that, how I found in the section, they're beautiful preserved fossils, plant fossils in here. That then, of course, are very good targets to extract for these biomarkers and the lipids. But also you found like whole tree trunks in the section. And if you look closely, you can actually see the paleo water horizon, so the groundwater horizon that was actually right here in that part. And that actually the roots are actually rooting into this kind of groundwater part. So this really shows you that it's very high standing groundwater in the section. So the tree trunk is right here further up. Okay, so next I will show you now the soil carbonate and the biomarker results in the section, and then also the volcanic glass that we derived out of the Angostura Basin. And in general, what you can see here, so just to clarify, so this is delta D here on the x-axis, and this is time, so 9 million years all the way up to 3 million years. And so on the left you have your lipids, here in the middle you have your carbonates, and here are your volcanic glass. And this we ignore at the moment because it's already the interpretation, but if you like to look at it, you do so. In general, you see several trends. So first of all, you see kind of a wettening trend, and just for clarification, so more depleted means wetter conditions, more enriched means drier conditions. And you see that in both proxies, in the soil carbonate proxy, but then also in the biomarker proxy. But then after that, you see a lot of wiggles in here in the section in both. Actually, we see a very variable isotopic composition of the environmental waters where both proxies were derived out of. However, at a certain point, you see a very large shift, especially here in the biomarkers, and you see this shift also in the soil carbonates. However, here we have much better resolution, so you see this much better in the record. And later on, you see a further basin aridification here, and that's especially shown here in these lipid biomarkers. So we interpret, we see two major events in the records. So one event we see in the record is really where we see very variable isotopic values in both records. And this is very consistent actually with a monsoonal kind of climate in the area. And we interpret that this is actually the onset of the low-level jet bringing moisture from the Amazon basin into northwest Argentina. So this is really the first time where we see this kind of low-level jet being active, because we come, the section below here is very arid. It doesn't contain any fossils, it doesn't contain any plants, it's interpreted to be very arid. And this is really the first time where we see a lot of moisture coming into the area. And this is also the time when we see all this vegetation developing, the alligator fossils occurring in the section, and really showing you that we have now a very wet climate. Later on here at roughly 6.5 MA, where you see this shift, this is actually in line with the uplift of the eastern flanks. So this is what I showed you, the orographic barrier towards the east, and actually uplift of this barrier. But you can see that this is a quite abrupt shift here in the biomarkers, and it's potentially due to the fact that we cross the threshold elevation. So in the Andes, the threshold elevation in the modern is between 1.5 to 2 kilometers, meaning when you have an uplift that has an elevation of 1.5 kilometers, you actually block all the airflow and moisture supply towards the backside. And that's probably the case rather when we reach threshold or cross-threshold elevations, because this is a very rapid, abrupt shift in the data. And if tectonic uplift, of course, occurs over longer periods of time, over millions of years. All right, so the glass itself, then here it's a little bit sparse data, so it's hard to interpret, but it seems to be more or less one isotopic value, but it's consistent with foreland setting. But then it actually shows a depletion later on when you form this orographic uplift. And here towards the top, you see this rapid increase again. And this is interpreted, and again, this kind of shift towards more depleted values. However, again, this cannot be topography or tectonics, an uplift, because this is a very rapid shift. So this would, if you would interpret it like that, it would be a rapid subsidence or loss in elevation, and then again a rapid increase in elevation that is hard to accommodate. So rather what is occurring here is probably the first time when we have a convective setting as similar as today in the modern. So this could be a time period where you have this convective setting as in the modern, observed in the modern. And this is also more in line also with the volcanic glass values that you find later in time. Okay, so with these biomarkers, we also, on the soil carbonates, you also can look at the carbon isotope values. And this is a plot just to show you the concept of C3 and C4 plants. So in general, C3 and C4 plants are actually controlled by the atmospheric CO2 concentration. So here on the x-axis and temperature, so on the x-axis you have daytime growing temperatures. On the y-axis you have the atmospheric CO2 level. And you can see here that when you cross a certain CO2 level or a certain temperature level, you cross into a C4 vegetation type, or this means how the plants are fixating carbon. And this you can see when you're looking at stable isotope values, or if they favor C3 vegetation. So this is the data of the biomarker delta-13C and also the carbonate delta-13C. And if you look at the carbon lipids, you see that there's not much differences, but then only here towards the end you see this kind of gradual shift in more C4, so this means more depleted isotope, so enriched isotope values versus depleted isotope values, indicating more C3. And this is really showing that there is less bioproductivity, so it means more arid condition, or there is a higher water use efficiency, but this means also that it must be much more arid. And the soil carbonate actually tracking quite well what we observe in the biomarkers, and this is one of the first data sets where you actually can compare both of proxies. And it has been questioned for quite a while if soil carbonates are really tracking vegetation. In this instance here in the Angastaco Basin, it is tracking quite well the vegetation that's occurring at the surface. And as well, you see this kind of shift towards more enriched values, also showing much more arid conditions. So again, so you see a very stable C3 vegetation, so indicating a wet climate until you uplift the orographic barrier, and then you see this kind of aridification on the backsides of this uplift, where you see less C3 vegetation or higher water use efficiency. So at the same time, I haven't talked about it here, there's also some clumped isotope temperature estimates, and I will not go into the details, but this is just confirming what we already see. You see a temperature drop right here, and then quite lower temperature, similar to what is observed in the intermontane basin zones today in the area. And in the foreland conditions, you see they are quite high, but fitting the temperature data is fitting because it's biased probably towards summertime temperatures. And again, here is like stable temperatures later on after you form your orographic barrier. So again, so this indicates really like that we reached threshold conditions of uplift after 6.5 million years, where we actually shut down the moisture supply into the intermontane basins. And that, of course, actually blocked also our drainage towards the east. And there is nice data by Mathis Hein that actually supports this notion that you actually lost connectivity, the direct connectivity towards the foreland at that time. But then later on, you increased actually the orographic barrier. You actually further aridify these intermontane basins over time. And then, of course, the filling with the sediments, this coarsening upward we observed. So this all comes back also with a concept proposed by Zobel, Hildy, and Strecker in 2003, where they proposed the concept of how you build plateaus outward over time. And the first step is you build like barriers, in this case here, these orographic barriers. You actually have fluvial connectivity towards the foreland. However, at a certain point of time, you lose connectivity to the foreland, where your fluvial system is not connected anymore. You aridify the backside of it, and then you actually start filling these basins up with sediments. And again, you form a new thrust that actually blocks moisture then from the backside. So with it, the whole vegetation is actually shifting slowly over time eastward and out of the way of the growing plateau, and with it also the precipitation that correlates where these uplifts occur. So then, of course, you fill further these higher elevations, and that's how you actually build out. This is one idea of how you build out orogenic plateaus over time. And there is a very nice study of these caimine fossils that we also found in this section. And you can actually see that, so these are section 1, section 2, section 3, and sorry, they are right here. So here at the top, so section 1, this location, section 2, section 3. And you can see that the fauna and also the animals are actually migrating with the tectonic uplift and dissection of these intermontane basins, and the foreland zone are always further eastward over time, as indicated here, where you find these alligator fossils. So in this instance, you find them in the Palo Pintado, then you lose them in the Palo Pintado, but then you find them in another section further east, and this process continues where you find them even further east today in the foreland. So that is the foreland record, and now I would quickly like to talk, lose a couple of words about our section that we have analyzed on the plateau, and compare then this with the foreland. So for that we went into the Pastos Grandes Basin and got a record that always was located at high elevation on the plateau. It has been interpreted like that. And again, to remind you, so our intermontane basin zone, our foreland zone. And let's go into the Pastos Grandes section that always was interpreted to be at high elevation of 4 kilometers. And so this is today located at 3.8 to 4.2 kilometers right here. And this is just to show you that there's a lot of deformation in these Miocene sediments. And we analyzed the sediments working along this kind of profile here in the Pastos Grandes Basin. And this is the most recent data, and this is actually no leaf wax biomarker data. And what is shown here is on the y-axis age, so the same time range from 9 till 3 MA. The delta 18O plotted here on the y-axis. And so we have our plateau record right here shown in orange, our foreland record shown in green. And as I showed you in this kind of cartoon, if you see differences between both records because they have the same kind of climate, then this difference can only be interpreted as elevation. So if you take the elevation or the differences between certain time periods, here you always end up with general a 50 per mil difference between the foreland and the plateau section. So, and what you see further is that this difference is the same over from 9 or 8.5 MA all the way up to the present when you look at modern stream water isotope values. So this means that there was always the same elevation difference between both sides. However, we know that our foreland setting was at low elevation and it's now at 2 kilometers. We know the section was uplifting at least 1.5 to 2 kilometers. And at the same simultaneously, both basins actually changed elevation at the same time. So that is really the most robust interpretation of this data set. Because, however, the most controversial part in doing paleo elevation estimates is really how you convert this kind of 50 per mil difference to an elevation, and because you have to know your lapse rate really well to do this. And nevertheless, when you take a step back and just look at the differences, you can see over time they mostly are not changing. However, we know there was uplift in the foreland. At the same time, you see that certain values are actually indicating much larger values here and differences. However, this could be the case that you actually have this convective setting not in place. So this is more like what you see today with the modern lapse rate. However, then there are times when you have a different lapse rate. Of course, when you do this conversion, you have higher elevation estimates. So to summarize all this part, the first thing that the hydrologic cycle in the Angostura Basin responded quite rapidly to topographic growth, especially as it crossed the threshold elevation, and that these uplift controls moisture supply into these into these intermontane basins and then into the plateau itself, and that the vegetation adapts quite quickly to these environmental changes. So this is so moisture supply into these basins are really controlled by this orographic barrier formation, and I showed you that this can be reconstructed with such a multi-proxy isotope approach. And what I haven't shown to you on time because of the lack of time is really that the transpiration and evaporation also, if you combine both proxies, respond differently to different tectonic forcings. So then lastly, I showed you the comparison between the plateau record and the foreland record. And this suggests that in this part of northwest Argentina, it seems to be that there's uplift of 2 kilometers. And then, of course, there's an eastward growth of the plateau in this case. And I showed you the use of this such a called delta-delta approach, but then also the strongest message is really that these basins were uplifting simultaneously over time. Nevertheless, how you do these calculation, paleo elevation calculation. So, and I leave you with that, and I say thank you.